Hello. Hello, everyone. Thank you for being here today. We'll have just one speaker, and it's my pleasure to introduce Lea. She's currently a PhD candidate at the Catholic University of America in DC. She obtained her bachelor's degree in astronomy at University of Maryland in College Park. And she's currently in her third year and is working on her thesis under the guidance of Dr. Steve Kramer. And she started her research by looking at the Star-Formation-AGN Connection using SDSS data, specifically working on AGN emission line diagrams. So she's currently working on the analysis of archival JWST data to investigate a spatially resolved view of the Star-Formation-AGN Connection in NGC 74 system. And in her free time, she's a competitive ballroom dancer. So welcome, Lea. All yours.
Your mic's on.
Yes.
Is
Is it on?
Try.
Is it?
Yeah,
Oh,
I think, yeah.
right. Is this better?
Yeah, it's okay.
Can you hear it? Okay. So hello, everyone. Thank you, Anna, for introducing me. So as she said, I'm a third-year graduate student at CUA working with Dr. Steve Kramer. And today I'm going to be presenting my research on a spatially resolved view of the Star-Formation-AGN Connection in NGC 7469. Once again, as Anna mentioned, I want to preface this with the fact that my research has been focused on optical and infrared data. And I really try to emphasize the high energy aspect of my research for this talk for all of you. Nope. There we go. So first, introducing NGC 7469 a little bit. It is a Seyfert 1.5 galaxy, which means that it has both narrow and broad components to the emission lines in the spectrum. It is one of the first galaxies that were observed with the IRS on the Spitzer Space Telescope. And something interesting about this galaxy is that while in the optical, it looks like a typical AGN, the infrared spectrum is dominated by the star formation that's taking place in the host galaxy. There is also a powerful starburst ring that's located right around the nucleus with a radius of about 500 parsecs. And the fact that there is this really strong star-forming ring right near the AGN makes this a perfect target to analyze the interplay between AGN and star formation. So for all of you, some overview of the X-ray properties of that galaxy. So soft X-ray emission lines were found both spectroscopically and using a 0th order image. In Medipur et al. 2018, they found that there was soft X-ray emission that is spatially extended from the central AGN source. And they found that this extended emission is also co-spatial with the starburst ring. They also found that the emission is consistent with emission from a collisionally ionized plasma produced by the strong starburst activity. But as you can see in the X-ray spectrum, the profile of the O7 triplet shows that there is also some gas that is photoionized in the center of this galaxy. Again, as you can see, this X-ray spectrum is pretty noisy, and we can't get a lot of spatial information about it or like kinematic information, which is why it's valuable to look at the same galaxy, but in different wavelengths, such as the infrared, which is what I am doing. So I'm using the mid-infrared instrument, or MIRI, medium resolution spectroscopy, that is on the James Webb Space Telescope. The wavelength range is from 4.9 to 27.9 microns, which is a very wide wavelength range. And it is an IFU, which means that we can get spatially resolved data. So unlike, for example, Spitzer, where you get one spectrum for the entire galaxy, we get one spectrum per pixel of the field of view, which are called spaxels. And the data that we're using was taken as part of the Director's Discretionary Time Early Science Program with PIs Dr. Armis and Dr. Evans. So I'm going to go over some work that has been done already with this data, both in MIRI and some in NearSpec. So as you can see here, this is taken from Dr. Armis's paper, where he looked specifically at the nucleus of the galaxy. And you can see in blue is the total MIRI spectrum. The dotted one is the Spitzer spectrum, and the red one is the nucleus specifically. The first thing that you can notice is how much better the data is between Spitzer and MIRI, with a lot of emission lines that appear that weren't present before, as well as the strong PAH features. I don't know if I can, oh yeah, I can, okay. Over here, over here, over here. And you can also see that they're not present in the nucleus. So there's very clear differences when you isolate the nucleus compared to the total spectrum. They also found in that paper indications of AGN-driven outflows coming from the nucleus due to the AGN, but they didn't do any spatial separation specifically, like taking advantage of the full capacity of MIRI. Next, there is also some NearSpec data, which we haven't looked into specifically yet, but will plan to do in the future. So just a little bit about what has been done with the NearSpec data. We have spectrum ranging from 1 to 5 microns. Once again, a lot of different emission lines that you can see, including some really high ionization ones like sulfur 9 up there. Where is it? Up here, and silicon 7 down here. And you can also see that those emission lines are only present in the nucleus and not in the star-forming ring. What they also found in this paper was shock-heated gas with the highest ratios to the west of the nucleus. And this will become relevant later. The next work that I want to highlight is work done by Vivian Yu, where they looked specifically at the distribution and the kinematics of the magnesium 5 line in the MIRI spectrum. On the image, you can see the contours of the magnesium 5 flux, and you can see that it is asymmetric with an extended coronal line outflow to the west of the nucleus again. And this extends to about 400 parsecs from the nucleus. The last work that I want to focus on is the work done by Lea et al., where they traced AGN feedback on the star-forming interstellar medium. Specifically, they looked at PAH features. And as you can see on the picture on the left, they used like the full resolving capacity of MIRI, where they were able to isolate very specific regions of the star-forming ring and compare the different regions. They also suggest minimal impact of the AGN wind on the ring, but we believe that requires further investigation. So just as Lea used PAH features to trace star formation, we can also use the Neon 2 12.81 micron line. On the left, you have our MIRI flux map of Neon 2, where in each spaxel, the Neon 2 line was fitted with Gaussians and then integrated to get the total flux of the line in that spaxel. There is also the contour overplotted on the Neon 2 image. And then I took those contours and plotted them on the HST F606W image of the same field of view. And as you can see, the Neon 2 contours overlap with the star formation that we can see in the Hubble image. 606W is a wideband filter, which means that we're going to be able to see the star formation, the continuum, like basically everything, including young stars and the O3 emission lines. So as you can see, we can use neon 2 to trace out star formation, but something that I want to bring your attention to is this hole in the ring to the west of the nucleus right there. And what we want to do is to use MIRI and different emission lines to figure out exactly what is going on, both in the ring and in this hole. And to do that, we can use diagnostic diagrams. So diagnostic diagrams in general are just plots that use ratios of emission lines that can be used to separate star-forming galaxies from AGN. And the most famous one is the Baldwin, Phillips, and Turlovich diagram, or BPT, which is used in the optical. But we also have some mid-infrared diagnostic diagrams that we can use. One of them is the Weaver and al. Diagnostic diagram, which is showed here, which uses neon 3 over neon 2 and O4 over neon 3. And just to give an overview of the plot, the top right corner is where all of the AGN, or most of the AGN live. The upper left corner is where the blue compact dwarfs and the Wolf-Rayet galaxies are. And the bottom left corner is where we expect the star-forming galaxies to be. So on this plot, every point is an entire galaxy, because this was made using Spitzer. So each point is an entire galaxy because we can't resolve the emission. Unfortunately for us, we can't really easily use the O4 line in MIRI because it's at the very end of channel 4 and is subject to a lot of fringing and PSF issues, which we will clean up the data eventually. But right now, instead, we use a sulfur-based diagnostic diagram where we have the sulfur 4 over sulfur 3 ratio on the x-axis instead of O4 over neon 3. So going over this plot now, each point on the plot corresponds to a single spaxel in the maps that are shown. They're not entire galaxies, now they're just single pixels. The stars of various colors correspond to the pixels that are within the area highlighted in the same color. So as you can see here, the star-forming regions, which are in orange and red, fall way within the star-forming region of the diagram, along with M83. M83 is a completely star-forming galaxy, no AGN, that was also observed with MIRI. And as you can see, they all fit well within where we would expect them to be. Our nucleus in pink and the region right around the nucleus in teal also fall right where we expect them to be in the AGN quadrant. And then the last thing that I want to point out is this region to the west of the nucleus, which we call the west wind. And it appears to fall a little bit between the AGN and the star-forming regions. So what we want to do is look more into what is happening here, especially by using higher ionization emission lines like footprint lines. So footprint lines are high ionization optical and infrared emission lines, which can be used to trace X-ray winds. These were coined first by Anna, which you all know, in her paper about footprint lines right here. So coronal lines have ionization potentials above 100 eV. So for example, magnesium 5 is a coronal line. And then a subset of coronal lines are footprint lines, which have ionization potentials above 138 electron volts. Two examples would be magnesium 7, which is available in the MIRI data, and sulfur 9, which is available in the NIRSPEC data. And those footprint lines work on the premise that different ions will be produced in the same X-ray emitting wind. So even if you don't have access to X-ray data, you can look at mid-infrared or near-infrared lines that will trace the exact same gas. And as an example, O7, which we saw in the X-ray spectrum of NGC 7469, peaks at the same ionization parameter as magnesium 7, which we have once again in our MIRI data. A lot of different models were done in Cloudy by Anna and by us, but they're very dense. So if you want to learn more about the modeling that went behind this, I encourage you to just look at Anna's paper. So now let's look at some of the lines that we have in our MIRI spectrum. So the 5 highest ionization potential lines that we have are iron 7, magnesium 5, iron 8, neon 6, and magnesium 7. Out of all of these, the only true footprint lines that we have are neon 6 and magnesium 7. And these are the total emission lines. So they were added through all of the spaxels for the entire field of view. And what you can see is as you go up in ionization parameter, the line profiles become more and more asymmetric. So for the neon 6 in orange and magnesium 7 in green, you can really see that blue wing on the emission line. And this blue wind is indicative of an outflow. And you can't really see those in the lower ionization potential lines. However, this is basically the stuff that you could see with Spitzer, where you have the total integrated line, although the data is slightly better. But now we have MIRI IFU data, which means that we can make maps of these lines. So these are our 2 footprint lines that we have, magnesium 7 and neon 6. Magnesium 7 is about 9 times weaker than neon 6, so you can't see as much, but you can see a little bit of asymmetry towards the west over here. But it's really more apparent in the neon 6, where you have this asymmetry towards the west of the nucleus with those contours. And just to emphasize it again with the arrow, it extends at about 100 to 200 parsecs from the nucleus. And once again, just to emphasize that we can use those lines in the mid-infrared and the near-infrared to trace out X-ray lines, we did some more cloudy models and compared the cloudy output ratios between our MIRI lines and the O7 X-ray line, just to see if they matched. And what we found is that there is quite a good agreement between the models and what we are actually seeing, again, emphasizing the fact that we are seeing the same gas. We can trace the same gas using different lines. So a little bit of a recap. So we were able to use high ionization potential MIRI lines to trace the X-ray wind. We also found that the maps show an asymmetry towards the west, again, shown by this arrow here, which was also suggested by our diagnostic diagrams with the west wind. And something else, if you remember when I pointed at that hole in the ring earlier, it appears that the wind is going in the direction of the hole in that star-forming ring, which could indicate an interaction between the central AGN through this wind and the gas in the ring. However, we can't really make any claims about this interaction until we do more data analysis, specifically kinematics, kinematic maps of the lines. And we are also planning on looking more into the near spec data. Specifically, all of the high ionization potential lines in the near spec data are footprint lines. So they're going to be really interesting to look at. And since I have like another minute and I removed that slide earlier, I'm just gonna go back to my sulfur diagnostic diagram and show you where the models lie. So this is our sulfur diagnostic diagram. This plot was made by Dr. Marcio Melendez. And as you can see, these are all of the cloudy grids for AGN. So these are exactly where we would expect AGN to fall. And that's exactly where our central nucleus is falling. So this proves that it's also backed up by modeling on top of just seeing how well our points separate. And I think that's it.
Thank you, Lea. Do we have questions?
Well, I do have an actual question first, which is, the spectra that you showed, I was wondering how much of the width of the spectra,
Sorry.
is instrumental, and how much of the width is instrumental and how much is real in these figures?
I don't know.
Okay. So I just want to make a point about the ring with the gap.
Yes.
This is a thing that happens in galaxies. So if you have a ring of dense material orbiting the center of a galaxy, if you imagine incrementing the density so you start with a ring that's lower density and perhaps it's accumulating material from outside and getting denser and denser. Up to a point, the ring will be smooth because the tidal shear of the region will tend to smooth out the ring, right? But as you add more and more material, eventually you'll get to the critical density in which the thing goes unstable. And you can actually calculate what that density is, and you can actually measure that density by spectral lines. And so what I'm wondering is, perhaps this ring has just gotten to the point where it's coagulating into a bunch of star-forming giant clouds and leaving that gap behind. You would be able to tell that by figuring out what the density of it is compared to the tidal shear of the region.
Thank you. This is work in progress. So if you guys have any suggestions, I will welcome them.
Any other questions?
So can you just make a map of the high velocity material? Just pull that out and see where it lies.
So like these?
But that's the whole line, right?
Yes.
Making kinematic maps that much more complicated, but getting redshifts and blue shifts or whatever. Can't you just cut out the piece that's in the asymmetric shoulder to the line?
Yeah.
And image that?
I could do that, yes.
Oh.
Yes.
Any other questions?
What are the velocities?
So this is going to be probably work that's going to happen with the kinematic map, but here you have like the velocity, just to give you an idea. But I think once we do the kinematic maps, we'll get a better idea.
Do we have questions? We have questions. Well, we are running out of time. So Lea is staying today at my office, B220, if you want to, if you have any other questions, if you just want to chat with her. And that's it. Thank you. And let's thank her again.
Oh, right.
Yeah.
Bye.